final talk of the session is going to be given by Osman Eldeş from Koç University. He's my MS student. And talk is about 3D autostereoscopic display using pico projectors and rotating screen.
Hello, I am Osman Eldeş. I am doing my master's degree at Koç University under the supervision of Hakan Ürek, which is also chairing the session, and with the assistance of my teaching assistant, Kaan Akşit. Today I will present you a new autostereoscopic projection display using a rotating screen. I have started this project as my bachelor degree thesis, and now I am still doing some work on it. Here is my outline. So first I will give a simple introduction and then I will tell you about the prototype that we have constructed, and we have done some crosstalk and luminance analysis, and then I will conclude my talk. So as you might know, there are a lot of autostereoscopic display techniques in the 3D society, and they have used different techniques, but most of them have create some exit pupils that will have the image content for one view and another, and create another viewing exit pupil for the content for the other eye. So, but the autostereoscopic display technique that we have proposed uses only two mobile projectors and then in-plane rotating screen. There is no translational movement, and it forms dynamic viewing slits which follows the viewer and provides large viewing area. So the problem is how we are gonna dynamically change those viewing slits. As you see, they appear on the viewer's eyes. So this is our results. So as you see, the viewer moved to the right, and the viewing slits also moved by rotating in plane. So this is some conventional methods. There is a multi-projector approach. So as you see here, the viewing slits are fixed. So how you are gonna carry those viewing slits to other areas so that the viewer can have freedom to move. So one approach is multi-projector approach. So as you see, they place many projectors in an axis so that they create many viewing slits or exit pupils in the viewer space. So when the viewer moves, she can perceive 3D image in a large viewing area. But the problem is they use many projects, and the energy consumption can increase, and it is a much more complex system than the proposed one. And the other approach is moving projector approach, as Mr. Sorman also presented in the previous session. They move projectors as the viewer moves, so that she can move in a large viewing area. But this also has some problems, and Mr. Sorman also pointed them. Like when you move the projectors, then the images must overlap on the screen, so that maybe you must decrease your resolution, or you must deal with the keystonings. So we propose another approach that does not require any projector movements and doesn't have any overlapping problem of the images on the screen. So I have proposed that what if we rotate those slits around the projectors, such that like this. So as you see, the viewer moves, and the viewing slits also moves with the viewer. So we achieved a large projection area without moving any projectors and any screen. Screen only rotation movement. Now I will show you the proposed system sketch. So we have two projectors which has stereo image content for the left and right images, and we have a screen. This screen relays those lights into two viewing slits. These two viewing slits, and we have a rotating mechanism which rotates these screens around its center, and we have a camera to capture the position of viewer. And this is the prototype that we have built. As you have seen in the previous one, we have a screen here, and we have a camera, and we have a rotating mechanism that rotates the screen, that is connected to the screen with a gear belt, and rotates the screen in plane around the center. And we have projectors, and the viewer is standing under the projectors, observes 3D. And the projectors that we have used is from Microvision. They are small and low powered. They high light efficiency and no imaging glass, so that we can move with the projectors. There is no need to focus. And but they are limited to 20 lumens. But since we have used a retroreflector screen, we can have a high gain screen, so it's not a problem. And the screen is that we have used for our project is a retroreflective diffusing screen. The screen consists of a linear diffuser which diffuses light in only one direction, and the retroreflective screen. As you see, when an incident light hits on the screen, it creates a slit-shaped light, so that when we project an image on the screen, we have those two exit pupils as a slit shape. And we have two screen prototypes. One is this one with 20 centimeter by 20 centimeter. It was the first prototype. Then we have built the second one, which has 50 by 50 centimeter dimensions. And this is a microscopic image of the retroreflector. It's a corner cube retroreflector. So this is the head tracker and rotating mechanism. Head tracking has been done by just a regular webcam. We have captured we know the position of viewer, and we know the position of projectors. So when we know the position of viewer and position of projectors, we can know the angle with the vertical line, so that we can rotate the screen by that angle. And how we rotate, we have a servo motor which is connected to screen by a gear belt. So by the information obtained from webcam, obtained from the position of a viewer, we rotate the servo motor, the screen. And this is how we have moved the viewing slits, explained in a schematic. So here we have two projectors, is placed by interpupilar distance. And we have a viewer who is standing in those viewing slits, and these arrows are the diffusing direction of the screen. So that's why the viewing slits are in the vertical direction. When the viewer moves, as you see, the projectors are fixed in that in these two images. When the viewer moves, we rotate the screen. So as you see, the direction of diffusing has been changed. So he is still in the viewing slits. And the reason why and the horizontal separation between viewing slits remains constant, this is actually a little bit confusing maybe for some of you, because when people think about rotating the screen, they thought that the distance between those viewing slits will change, so that it will not be interpupilar distance anymore, so we will not be able to observe 3D. But since the projectors are fixed, they are like anchor points of those beams, so the horizontal distance, at least in the horizontal axis, doesn't change. So we have a limitation here. So when the viewer tilts his head, then he will lose, or maybe he will the brightness will decrease. But as long as he is on the approximately the horizontal axis, it will not change. And we have set the interpol distance as 65 millimeter. And this is the working prototype. I will show you a video of the working prototype. Okay, I should pay, I guess. So here, I'm moving in the viewing field, and the camera captures me, and the mechanism rotates the screen according to my positions. And this is the view from the right eye of the viewer. Okay. Here I am capturing the viewer's eye, so that we can see how the viewing slits dynamically tracks the weaver. And this is, as you see, as the weaver moves, we still see our ladder. There is also a left ladder is projected on the screen. Sometimes we see L ladder because we have some we had some mechanical problems. Since the screen is huge, we needed to have a strong servo motor because it swings when it moves fast. And the other reason why we do it slow is but we could do it faster with a strong motor. And this is the how dynamic VXLS tracks the weaver. Here, he also, in order to record the screen, is holding a camera. Here you see two bright lights follows the weaver's eyes. So, and as you see, the weaver moves and changes its position, but since the weaving cells are always on the weaver's eyes, it doesn't lose any image, and there is no discrete transition between different perspectives. So it's smooth transitions between different perspectives, and he could also move up and down since the weaving cells are long enough. And this is how actually the screen looks like. The both images has been projected on the screen, but since it's a little bit complex structure, and due to the low crosstalk levels, we don't see the left image, we only see the right image. We have those little lines on there, but because we have constructed the screen with six triangular retroreflector. This is a screenshot for the one of these. And we have done some crosstalk experiments. So this is our viewing area, and this is the projector, the position of projectors. So this is the weaver space. So what we do, we have placed cameras in many different positions in the weaver space, and we measure the crosstalk values. So how do we measure the crosstalk? We define the crosstalk has been defined as leakage over signal times 100, the percentage of crosstalk. So leakage means how much the light leaked from the right image to my left eye, or to left image to my right eye. So that we have projected black image by left image and white image by the right projector. And for the signal, and this is actually this is for the left eye crosstalk value. That's why we have projected white by right projector to get leakage. And for the signal, we reverse the images. We project white image by left projector for the left eye, and by black image by right projector for the left eye. So we obtain some values and we interpolate them so that we have achieved the crosstalk map over the weaver space. So as you see, the crosstalk is below 5% in this area. And this is the below 4% of crosstalk and 3% of crosstalk, and it is very low when you are really close to projectors. So, and when we define the optimum crosstalk value, of course the optimum is 0, but under the 5% is acceptable, as the literature says, the crosstalk value. So the acceptable value, for the acceptable value, we have almost 50 centimeters by 50 centimeter weaving area. And this is the brightness values, luminous values. As you see, the brightness is so high when we are close to projector, and it decreases because of the beam profile of the linear diffuser. It had a 40 degree, as you see, the diffuser that we have used was a periodic diffuser, and it has a 40 degree diffusing angle in one direction and 0.2 degree diffusing angle in the other direction. And when we calculate the projection distance and the diffusing angle, it's approximately the same. So the experimental results classify the theoretical results. But what if we want to reduce the crosstalk values, or we want to have a larger weaving area? And this is the effect of weaving slit rotation over crosstalk. So now I will come to the crosstalk analyze again. So as you see here, the crosstalk increases when this width of weaving slit increases, because the width, when the width is so large, that light will come through the other left eye so that it will leak more and the crosstalk will increase. When we rotate the screen, the actual width doesn't change, omega, but the hash changes, the horizontal width, because there is a, as you see, a relation like hash equals omega over cosine alpha. So when it rotates too much, then the too much rotation results in crosstalk, because the hash would be greater than 2 IPD, 2 interpupillar distance, so that the image for the one eye will leak to the other eye. And we have a maximum rotation angle by omega over 2 IPD, arc cos omega over 2 IPD. So what we need to do to reduce the crosstalk, we need to reduce the omega. So how do we reduce the omega? I have said this is the 0.2 degree diffusing angle in one direction. So we must reduce this diffusing angle, or we could also this diffusing angle. So we have used another diffuser that we have took out from a regular laptop screen, and it's around almost 0 degree diffusing angle. It's a periodic diffuser, 20 by 0 degree periodic diffuser, and we have also analyzed its crosstalk and luminance values. And as you see, the crosstalk values has dropped down to 3% from the 5%. And if we define the weaving area as the area that is whose crosstalk values is less than 5%, we have increased our weaving area. It was 50% by 50 centimeter by 50%. Now it is almost 70 centimeter by 60 centimeter. And this is the brightness value. Since the diffusing angles are small, we have more brightness. But we could have more, but since we have used a 20 lumens pico projectors, and we didn't use the whole scan angle, we have placed it around 120 centimeters away from the screen, so we could have around 1 meter diagonal screen, but we have only used 20 by 20 centimeter screen, so we use only a small portion of the power of the projectors. That's why the brightness values are not that much. So, but it is higher when you adjust the scanning angle too. And we have used the same crosstalk analysis, of course. And this is the comparison between diffusers. First, we have used that 40 by 0.2 degree aperiodic diffuser, and then we decreased the diffusing angle, and we achieved a more rotation angle, so that we achieved a larger weaving area. First, it was 46 degree rotation angle. Now it was 58 degree rotation angle. And we reduced the crosstalk values. And actually, this is conclusion, but I have actually 2 more slides that I have hide because I hope maybe it's better to mention those. With the experimental results, we also done some theoretical works, such as how do we calculate the weaving slit length, or how do we calculate the maximum rotation angle. Actually, I went through the maximum rotation angle. So the weaving slit length, and when we did this theoretical calculation, we saw that there are actually a lot of trade-offs between different parameters. Like when we want to have a more bigger weaving slits, we need to increase the projection distance. As you see, the equation is 2 times d times tangent phi. Phi over is the diffusing angle over 2. So if we increase the d, we will have a larger weaving slit. But then we will also have a larger weaving slit length, weaving slit width. So our crosstalk values will increase. And so this is the for maximum rotation angle I went through. And there is also another actual parameter that I want to say. The optimum position for the weaver in the z-axis is he must stand over just under the projectors. So this is the best position that the weaver observes the screen, because the screen relays images on that plane of projector pair. But it has it allows some movement for the weaver too. So this is a simple triangular similarity. So from the S over omega, omega is the width, S is the screen. We achieved that one, that equation. So the depth of weaving slit, the allowable movement in projection axis, is defined by d, s, and omega. So when we increase the omega, we will have more freedom to move, but then we will have more crosstalk. When we increase the d, we will have more freedom, but we will have more crosstalk too. So these are also theoretical results, and the experimental results fits with the theoretical results. And we have submitted a paper for Optics Express, which will be published soon, I hope. And this is the conclusion. We have proposed and built an immersive display. It has a full resolution, full color. It has a high gain screen, and there is no discrete transition between perspectives. Fixed projectors, but we don't have any problem with overlapping the images. Or fixed screen, maybe it rotates in plane, but it doesn't make any translation movements. And we have done crosstalk, and luminous analysis is less than 5% in a large viewing area. And possible applications I see is like a passenger screen and automobile zone in screen, because it only aims for single viewer. The applications must be aimed for a single viewer too. It can be a passenger screen that we see in automobiles, and training or entertaining simulators, or a CAD design tables, maybe by back projection. It also allows back projection by using a different screen. So thanks all for your attention.
Okay, we can take questions. Yes.
Yes.
What's the resolution of the images?
The resolution of images, actually the resolution of Pico projectors is 85 by 850 by 500 resolution. It is a wide VGA, but we didn't actually characterize the effect of retroreflector and the diffuse screen on the resolution. But the projected images are 848 by 500.
Does the rotation speed influence on the quality?
Actually, the screen does not rotate continuously. The screen rotates with the when the viewer moves. So as no one has stated that it decreased the resolution or it decreased the quality. Actually, we have tried with different viewers, and we didn't observe any decrease in the quality.
Okay. Last question? Yes.
The actual diffuser material, is that just a commercially available?
Yeah, that's a commercial. We have purchased them from Luminit. It's an aperiodic diffuser. We have used also a periodic diffuser, but since the retroreflectors are also periodic and the diffuser is also periodic, there occurs some moire patterns or fringes. So that's why the periodic diffuser diffuses less in the horizontal axis or in the minor axis, but it occurs some moire patterns. So that's why we have choose the aperiodic diffusers, so that we get rid of the moire patterns.
Okay, let's thank all the speakers of the session. We can close the session.